The speaker of today's HPlan workshop is Malik Ghallab, a speaker who needs no introduction, but I will still introduce him and be as brief as possible, which is not easy because he has a long list of achievements. So Malik is no stranger to us. He has been active in knowledge representation and reasoning, planning and learning of skills and models of behaviors, and he has advised so far 32 PhDs. He was also giving lectures in several prestigious French engineering schools, among which is Isaïe Supérieure, which is also his alma mater. He was director of several AI research programs in France. He was director of LAS CNFS and CTO of INRIA. He also chairs the steering committee of ANITI, the Interdisciplinary AI Institute of Toulouse. He is also ECAI Fellow and Dr. Honoris Causa of Linköping University in Sweden. Last but not least, he authored many papers and books. Two of his most famous books are Automated Planning, Theory and Practice, and Automated Planning and Acting, which are textbooks in AI planning highly regarded and cherished by many of us here. While I've never had the opportunity to work with him, I know some of his colleagues and students. And according to them, he is very passionate in what he is doing, yet he is humble, friendly, and supportive. His knowledge is admirable. He can talk very theoretical to you, and at the same time, he's very much into planning applications, especially for robotics. So today, he will talk to us about planning for the purpose of acting, while using hierarchization for the reasoning on actions and execution of actions. The talk is based on some recent concepts and development on operational models, refinement acting engine, and a Monte Carlo tree search planner, UPOM. Let's enjoy the talk from Malik. You may ask questions on the chat or later in live during the Q&A. So please, Malik.
Thank you very much, Jean, for this very kind introduction. And thanks to all the organizers for this interesting workshop. Good morning, good afternoon, everyone. In this talk, I would like to share with you my belief that beyond handling such complexity, hierarchy is critical for the deliberation of a cognitive agent, and in particular for the integration of planning and acting, which is the focus of my presentation. So hierarchy is critical in computational thinking, as discussed in this well-known paper by Janet Wing in 2006. She says that computational thinking is using abstraction and decomposition and thinking at multiple levels of abstractions. And these multiple levels are hierarchy. We have hierarchies ubiquitously in computer science. Almost every concept X, there is a hierarchical X for it. And beyond computer science, in computational biology, we are now able, there are authors able to explain why living systems have hierarchical organizations. So in this paper in the Computational Biology Plus journal, it says, the author says that living systems evolved to be both modular and hierarchical. And they found out that hierarchy independently improves adaptability of living system after controlling for modularity. In planning, we also have a long history of work focused on hierarchy for taming complexities. This is what is motivating this work by Stuart Russell and his co-authors about angelic hierarchical planning that you are probably aware of. So in hierarchy in planning for taming complexity, we have a long list of hierarchical planners. I'm referring to a few of them here. The pioneering work by Earl Sacerdote in the early 70s and by Austin Tate and his co-author, Noah Nolin Opland, the work by David Winkles in the 80s, by Denano in the 90s. All these planners and many others that I didn't mention here have been used to address significant applications and very important applications in planning. Most success stories in planning rely on hierarchical planning. We also are familiar with several fundamental contributions regarding state abstractions, regarding task hierarchies. So I'm referring to some of the contributing authors on these aspects, but there are many, many others. It's not a survey that I'm giving here, but my motivation is to build on top of these fundamental contributions, not only for planning, but for the design of a cognitive agent, acting in its dynamic environment and reasoning not only on what to do, but also how to do things for achieving its objectives. That is, this actor is performing things through some execution platform that we see here, interacting with through actors and sensors with its environment and getting tasks to perform from users. And this actor has a hierarchy of deliberation loops that allows it to handle not only the changes in the environment and its task, but also how to adapt to what's going on. So this is the kind of hierarchy I'm interested in, and this interest goes to for many, many years. In particular, I have contributed with Denano and Paolo Traverso to a position paper in 2014 that developed the view that there are two interconnected design principles for the design of such an actor, which are to follow a hierarchically organized set of deliberation and to perform continual online planning and reasoning. This position paper argues that this hierarchical deliberation process differs significantly from hierarchical planning alone for reducing search complexity offline, because it's not the same purpose, the sole purpose, and because we are interested in heterogeneous representations. So my focus here is more on the online integration of heterogeneous reasoning functions for these deliberative agents and less on handling huge homogeneous search space. Basically, I'm not considering a very large search space, which is certainly an important issue, but not my main issue here. So since this position paper, we and others have tried to address some of the challenges underlined in this position paper through a following approach. This approach goes back to a book chapter that I'll refer to a couple of times, and to several papers, most of which have majored into this recent paper that you can find in the AI journal with my co-authors, and I refer to in the abstract as well. The approach relies on a refinement acting engine, which is the main piece or module in the approach that interact through sensors and actuators with the environment and interact with users. It relies on a library of refinement methods, and it maintains the current execution state of what's going on in the world. And it also relies on a receding horizon anytime Monte Carlo tree search planner that we call UPOM, that advise the actor and the refinement acting agent about what's the best method to pursue in order to advance its task. And it records its successful runs and use these records to learn heuristics useful for its planner and to learn a base policy. So this is the global view, and that was my introduction. For the remaining of this talk, I would like to present the refinement acting engine, then to present the planner, the anytime MCTS optimizing planner, a few things about learning heuristics, a few things about results, and then I'll discuss limitation. If I have time, I'll share with you some of my intuitions about how to handle these limitations before concluding. So that was the outline of my talk. And as Pascal and Jean said, you are welcome to put questions on the chat while I'm presenting. So let's talk about the refinement acting engine. As I mentioned, it relies on a platform that offers sensors and actuators, and it receives from these platforms events and from users tasks to which it has to react. And we want it to react not only on a reactive way, but on a deliberative way. And it uses for that a library of refinement method. So basically, this system select methods for addressing current tasks, subtasks, and events. And many of these are running on concurrently. It progresses in parallel the topmost method in each refinement thread. The refinement thread addresses a top task or events to which this refinement acting engine has to react. And this progression of a method takes into account normal computational step assignments and so on, control steps, and primitive actions, and recursive further refinement into subtasks associated to the current task or the current events. And if there are failures, and there are certainly in an open environment cannot run without failures, there are certainly failures to which the refinement acting agent should be able to address with by retrying other methods that are applicable to the new context for this failure. And there are concurrent threads of different refinements that handle new tasks and events. So basically, the main point in understanding this refinement acting engine is to discuss a bit the representation and the main aspects of the procedure. The presentation relies on refinement methods. A refinement method has a role which says which task or event it is defined to address. It has a set of preconditions, and it has a body. Every element here relies on parameterized state variables with variables that are local to the method and correspond to, for example, several instances here of a robot or a door, robot R or door D with some conditions. And the body is a piece of program that has, as you see here, some classical constructor, while loop, and if then else clause. And this task, in this simple example, how to open the door, is refined into several tasks, depending on these conditions. And it also uses a number of primitive actions, such as the one in green here. And each of these tasks has, for example, the task unlatch has also different methods that may be used to address it. And each method is also using subtask, subtask and primitive actions to go on. So these are basic concepts that you probably are familiar with HTN. I'll underline what are the differences with respect to HTN. Here, this is a method to deal with a specific event, some emergency. So I won't detail formally the representation, but I believe you have an intuition of what's in there. So basically, the body of method is the program that refines a task or an event into a sequence of statements, refinement steps into subtasks, and primitive actions with recursion and iteration loops. The primitives are non-deterministic actions. They include sensing, epistemic actions, they include commands to the platform, and once an action is triggered, the actor remains aware of its status, such as it's still running, it has succeeded, or it failed. And the actor is running several such threads of ongoing tasks and reactions to events that are concurrent with limited handling of possible conflicts through methods. More can be done on that, and this is one point of the open issues. And as usual, for any Turing computation, in order to be able to prove anything, you assume some finite execution. The main difference with HTN here is that the body of a method is a Turing complete program. And the second main difference is that the primitives are non-deterministic, and you need to take into account this non-determinism. It cannot be deterministic actions because you are reacting in an open environment, you are interacting with users, and your actions and the environment is not completely defined, and you need to leave room for non-determinism. So these are the main two differences: Turing-complete bodies of methods that are programs and non-deterministic primitives. So given that, the main function of the refinement acting agent is an infinite loop, while loop, that takes into account any new task or event to be addressed. It observes the current states and select a method for these states. And then this method will be progressed. And for each, and it puts that into the agenda. The agenda is all the threads that needs to be progressed by the engine. Classical notion in AI, the agenda is what needs to be done at some point. So a collection of concurrent threads. And for each element in this agenda, or for each thread, you observe the current state and you progress this state C with respect to the state of this element in the agenda. I won't detail the data structure, but the basic idea is that if this is an empty set, then you have nothing to do, and you have succeeded because this part of this particular thread, not in this particular thread, there is nothing that remains to do, and otherwise you run into a failure and a retrial is needed. So two main points to underline here is that the state is not progressed through simulation, but through observation. This is what the execution platform tells you, and you have to select a method to progress each element in this this thread. So the progress function advances in the current method depending on this step of the method M of I is an already triggered actions, some assignment steps, or a primitive action, or a task that in which the current subtask needs to be refined recursively. So if it is an ongoing actions that failed, you have to retry. Not much needs to be done. If it is a computational step, you just perform it and advance. If it is a new primitive action, it has to be triggered, and you will check at the next iteration whether it is still running, it's been done, and you advance in your stack, or you need to retry. And if it is a recursive refinement, then again, you observe the current state, and with respect to this state, you select a method. So this select method is something very important that for which you will need planning. And retrial is again observing the current state and selecting a new method with respect to the new state of the world. You do not backtrack by going back to a previous state, because you cannot do that in the real world. Not possible backtracking in the real world, but you can redo some actions with respect to a new context, and then other methods may be applicable. So this is the main element in the reactive refinement acting engine, and I would like to mention that it is based on a well-known procedural reasoning system called PRS that has been around and tried in many of our robotics experiments that has been developed by my colleague Felix Ingrat, and benefited from Felix by many fruitful discussion about the definition of what I just presented. So basically now let's focus on how this refinement acting engine selects what's to do. So basically, this is the second step of planning. You would like to be able to, given the actual context, to reason about what are the options offered to you and select the best option. And the idea here is to perform some optimization. So let me underline two things: what's in the context, and what is this M star, the best method. What are the notion of the best method? So the context is the current refinement stack and task. what's going on, where am I, what is the current task or subtask, and how it relates to the stack of pending tasks on which I need to progress. But there is another important point in this context, is that this context relies on an abstraction of the current acting state. Here again, I have a hierarchy. The acting state takes into account all what has been observed, and it can be continuous and so on. But the planning state on which the UPOM planner will reason is an abstraction. And in this abstraction, you are relying on parameterized state variables. Their domains in the acting state can be quite complex. You will simplify them in the planning state if needed. And you may also ignore some state variables in XI because you do not need, or you do not have means to simulate them in the planner. So basically, the acting takes into account all what the execution platform is able to perceive and report about, while planning abstracts some of this, and you perform your choice of the best method with respect to this abstraction. So UPOM changes its state through simulation, while RAE changes its state through observation, and underline this, the need to observe what's going on at each choice, at each step of the RAE, while UPOM relies on simulation, and simulation is an important aspect of this approach. So this is the context. Now, M star is basically a mean to get the optimal method for the current context with respect to some utility criteria. So we are in an optimizing planning approach, and let's see how you do that. Selecting the minimal cost method is something that can be done easily if you assume that there cannot be a failure. So assume that you have a cost distribution of performing some primitive action A in state S that leads to state S prime, and these are positive costs. So the cost of advancing in a method M for a given stack in a state S is, if it is simply a computational step with an assignment, is the cost of the remaining part of the method. If it is a primitive action, it is the cost of this action plus the cost of the remaining part of the method. Otherwise, if it is a recursion with a new refinement, then there is a push on this stack, and you will see the pursuit of the current task later on. But for the moment, you will deal with the upper new subtask on which you refine. And if you have finished your stack, this cost is 0. So this is the basic definition of your cost given the formalism and the representation. And from this basic definition, the optimal definition comes easily using the optimality principles and an extension of the Bellman equation. So this optimality principles is basically the same thing here, plus a weighted sum, because this is a non-deterministic probabilistic action, and you will rely on a weighted sum of this expression over all possible outcomes of these actions. So this is something you do in MDP planning in a classical way. And here it is a refinement, and this refinement may offer you several such method M prime, and it is a minimization. That's where the optimality principles plays in. It is a minimization over all applicable actions. So this was the case without failure. In general, you may have failures. As I mentioned, you should expect failures and be able to retry again and do other things. So the cost of a failure is infinite. So in order to be able to advance with the optimality principle, we will rely on the maximization, not minimization of a cost, but maximization of some utility functions. And we have tried a few. For example, the utility U being an efficiency, which is the inverse of the optimality. If the state to which your action led is a failure, then this utility, this efficiency is 0. Otherwise, it is the inverse of the cost. And now you have something that is compositional, and you can combine the utility of several such steps in an easy way, which is developed here. I'm not going to detail. And this combination operators is associative, as you may expect, in order to be able to perform to rely on the optimality principles. Basically, that infinity is the neutral element. Gives you back to the same value, and if you have a failure either of an action U1 or with respect to utility U1 or U2, then if you have a failure of an action, the utility is 0 and the composed utility is also 0, because you need both actions to succeed. On the basis of this, I mentioned that we tried also a success ratio that I'm not going to define here for the sake of time, but on the basis of this, what I presented as a cost can be easily generalized as a utility function, which is the utility of the next step if it is just a computational step, which is the sum of the utility of one primitive actions plus the utility of the remaining, or which is the utility of what you push into your stack. And applying the optimality principles, you come up with the optimal utility with respect to a weighted sum, giving the probability of an action, or the maximum U star with respect to all the applicable methods. It's a bit technical, but I hope that you grasp the intuition. And from this definition, the normal way for the actor is to perform the optimal method. And the optimal method is just the argmax with respect to this function. All this development was in order to be able to define some M star. So basically, this is how you define, you select a method. How to find M star? Well, you could put together a direct implementation of equation U, which is by using dynamic programming. Basically, you extend the main algorithms of dynamic programming in MDP to this formulation, but it's certainly too complex and not compatible with the principles of all-line reasoning that I mentioned. So you have to rely on some estimates. And the best way to do this is to use Monte Carlo tree search techniques. And the advantage is you keep a full control of your search parameters, and you can perform anytime planning. And you can also prove the asymptotic convergence. In order to do that, you have to adapt the MCTS techniques that are used in MDP to a particular search space that I'm going to mention quickly. And you have to be able to perform a sampling of the outcome of an action through your simulation or through an a priori definition. So basically, the MCTS algorithms for Markov decision process is that for an action, you have a distribution of possible outcomes, and you have to search such space with stochastic search planning algorithms. So running MCTS rollouts, you can use a single rollout, that is for each available actions or applicable action. You perform a rollout, you compute the value or utility, or in my case, the value, your utility function with respect to this choice and all the remaining steps here. That you did in a rollout, and this qualify A1, and you do the same for all available actions, and you choose the best. In multiple Monte Carlo rollouts, you have to keep in mind that this action may have several possible outcomes, and you are going to try several according to the probability distributions of the outcome of these actions. And a good strategy for doing this is UCT, which maintain a trade-off between exploration and exploitation. The point here is to extend UCT to a particular search space. This search space have 3 types of node. You have a task, and for this task, you have a disjunction node with several possible methods. For a method, you have several steps. That if you consider a flat execution, you will see that in this particular context, this method will develop into a sequence of steps. Some of them are not shown here because they are internal computational steps that you don't care, but some of them are important in your search space. These are your primitive actions that are non-deterministic, may have several outcomes, and these are your recursive refinement steps where you have a subtask, and for this subtask, again, you have several possible methods and so on. So basically, your stack here at this point is that you have been dealing with this task 2 with a method M, and you are in step 2 of this method. And in this step 2, you have a new subtask to 1 for which you have been you are using M1, and you are, for example, here in the 3rd step of this method. And this is what I call a stack, and how you compute your rollout and your utility with respect to this rollout. So basically, your stack in the search space is a task, method, which step in the method you are, and what you have tried. I didn't mention that, but for retrial, you need to keep track of what you have already tried. Basically, if I am here, a rollout is that I have tried this action, and I suppose that its outcome is 1 in this particular rollout. I'm trying this method, and in this method, this action led to some step 2, and I have here another step 3 that is a refinement with a number of steps and so on. And then I went through all the remaining steps of this method until the last one, etc., until some maximum depth. So a given rollout can be something quite complex in this refinement tree, and you have to keep track of it. And this is what UPOM does. UPOM start with the select function that array needs, and these select functions check what is applicable in this particular context. It abstracts away the current state into a state needed by the reasoning planner, and it will use a Bayes policy with respect to some heuristics if it is interrupted into some anytime progressive deepening loop. So you start with a first estimate, assuming that you have a heuristics, and then you go deeper and deeper in your rollouts. So, and at each depth level, you perform n rollouts with a function UPOM with respect to this particular stack, and this gives you an improved estimates of your best actions, and you keep doing this until a maximum depth. And that is UPOM. I'm not going to detail every step of it, but I would like to underline that this is the UCT trade-off step where you combine the quality of your current method M with respect to exploration exploitation. And this step here, in this step here, you estimate the value of the current method MC plus the utility of remaining part of the rollout average over all previous rollout for this method, in order to be able to choose the best one at the end. Lambda is just what the value returned by UPOM one step further. And you do that for the various cases of the step you are in, whether it is a non-deterministic actions, whether it is a refinement actions. So the properties of this planner is that you can prove the asymptotic convergence in static domains. We did a proof that in the paper I mentioned, there is a proof that is proposed in static domains, that is for domains where you have no exogenous events. I believe that we can extend this proof to the case where you have exogenous events if you can give a distribution of these events and with infinite depth. Giving that, if your number of rollouts grows to infinity, then the planner reaches the optimal method. The method estimated by the planner is the optimal method. The important point here is that it can be interrupted anytime, and its complexity depends on your search parameters, the number of rollouts at the maximum depth, plus the number of applicable actions. So you have a full control of its complexity. Now you need heuristics, and the learning will allow you to estimate these heuristics, and you rely on an incremental training set of successful runs that will allow you to get a base policy or heuristics in order to cut your depth at any point. So you can define heuristics by hand, human specification that are either domain specific or domain independent. Domain independent techniques appears to be too complex. We didn't try it, given the kind of search space that I just mentioned, but you can rely on machine learning for domain specific heuristics. This is what we did. We just recorded successful runs and took into account using the standard learning tools, took into account the performance with respect of our utility functions of the various options available at some point. And two learning strategies have been acquired. One that gives you a policy that tells you here is an estimate of the best method given this task and state, and another one is a heuristic function in the usual sense, which estimates the utility of your method in some state for a given task. And and these are the two learn by and learn H. Basically, this can be extended for incremental learning online with planning and acting. You can rely on an initial training set where you run RIA and UPOM online, either without heuristics with unbounded depth for this initial training step, or with some hand-defined initial heuristics from offline learning on simulation or on training runs. So this is to initialize your learning, and then online acting, planning, and incremental learning, you augment your training set by recording successful runs, and you keep track of the utility values, and you use that to update both the learn by and learn H, and you switch to RIA to use either this one if you have no time for planning, or to use that one with UPOM if you have time for planning. And you repeat the above steps every X run in order to improve your heuristics. So some results. We tried different simulated domains. Most of them are quite simple. I'll say a few. This is an exploration domain. This picture was taken in the south of Morocco with robots from our lab. Experiments performed by Simon Lacroix and his group. Actually, they didn't use the material I'm presenting. We relied more on simulations of the domain than on actual robots. But there is a current collaboration with Oskar Lima and Joachim Erzberg, a group at DFKI in Germany, with Sunandita Patra in order to implement this on robots. The other simulation domain is classical search and rescue domain, a domain where you have a robot that has to fetch in some environment, different kind of object and service. This object, you have a multi-robot navigation domain where robots have to help each other in order to go through this environment. And we have something classical RoboCup logistic domain where you have to deliver various parts to various machine at some point. So these were simulated domains. Again, none of these domains were run on physical robots, but collaboration is going on. Some of this domain will be presented by Sunandita Patra in the demo session in 3 days from now, or 4 days, I believe. So for all these domains, there are exogenous dynamic events. You have concurrent tasks, and for most of them, you have dead ends, you have sensing actions, and you have several robot collaborations that are simulated in these domains. The number of templates for tasks for methods and for primitive actions in these domains are not very big, but the number of instances of tasks, possible instances and current instances run in our experiment of tasks of methods and primitive actions can be very large, as you can see. And the search space, the upper bound on the search space, as estimated, can be huge, or even in this case, because we have continuous variables, non-finite. So these are the features of the domain. Some 12,500 runs have been tried, 2,500 for in each domain with several tasks and events, and with the number of rollouts between 1 and 1,000, and the Dmax between 0 and unbounded depth. Actually, the maximum depth is not very deep in these cases. The average computation time per task in second is not very important, in the order of 15 seconds. This is purely a reactive array. You can see that it doesn't need much time. Average out over all this domain, whereas when you perform UPOM with unbounded depth, there is some computational cost, but keep in mind that you are acting in a real environment, and this cost can be performed in while you are running actions, and the actual actions execution of this action takes much longer. So basically, you will see the performance in a moment. The learning was done with a training set of 540 problems, some 130 problems per domain, and many runs in each of these problems. The results are detailed in the papers I mentioned. Let me just here underline that in green here for the various domains, you see the base case of the efficiency of the system while running just array law. And in purple here, you see it while running UPOM to full depth. And in yellow and green here is using LearnPy, the base policy, or using limited depth with LearnH. And there is a significant benefit with respect to the base case in most of the domains we have tried using Heuristics or using the planner. So these were some of the results. Let me underline limitations. I see that I don't have much time to get into the details of this limitation. I'll skip through them very quickly to share with you some of my intuition about how to handle them. In the survey, in the position paper, I mentioned earlier about how to design a deliberative actor. A number of open problems have been underlined, some of which have been progressed through the methods I mentioned, but there are others that have not been covered yet, such as handling space and motion reasoning, handling temporal reasoning, which is not part of I just mentioned, learning refinement methods, which is something very important, and addressing a more comprehensive deliberation, not just acting and planning. A few intuitions about each of these open problems. Space and motion planning is certainly something the easiest to implement. You rely on a representation with labeled CAD models with classical things for computer-aided design systems, and for also handling geometric state variables when you are dealing with motion planning. Such as the position of an object on some surfaces, whether it is in some containers, and so on. And you have to take into account reachability, visibility, and the nearness of obstacles, and so on. And you use motion manipulation action, and you model them, and you compose them into observation, precise metric position in order to be able to plan, and motion manipulation planning procedures with the usual probabilistic roadmap or stochastic and stochastic search, rapid random trees, with heuristics to optimize for these metric parameters. And then you control along the trajectory. This space and motion reasoning is easily adapted to the actor. You have to assume reversible motion. You perform a motion that doesn't succeed, and you retry, which is the usual case. And it's not something that you would use for a very tight constrained environment. And the processing in RAI, you have to revise the progress procedures that I just presented, taking into account possible failures in motion planning, because motion planning can be retried with more sampling again, and you also should be able to handle action retrials, motion retrials prior to the retry method. For UPOM, you do the same thing through simulation of motion, like you simulate any other actions. You can rely on some shallow simulation, which is basically probability distributions of the possible actions, or deep simulations. We have simulators that can run motion planning on expected state, and with a possible backtrack within the MCTS rollout to optimize this choice of the metric parameters. You can also extend LearnPy and LearnH to metric parameters, and you have to tune your motion planning strategy with a probabilistic roadmap and rapid random trees with respect to your simulation steps that can be quite costly, and with respect to motion planning that works fine in free space and much less in clustered obstacles. Regarding temporal reasoning, I believe I'm running out of time. I'll just mention the main things, main idea, using, in my intuition, that the best approach is to use temporally qualified state variables and a basic specification for your primitive actions that are the usual deterministic specification of temporally qualified actions within this representation, where you assume that many things can happen while the action is going on. And for the non-deterministic primitive actions that we have, then you rely on multiple specification with the probability distributions for each one. So this can be quite heavy, and it needs certainly learning in order to get this multiple specification. Alternatively, you can have something which can be also multiple specification with just a precondition and the distribution of possible effects with this temporal representation. Concerning the methods, basically, you have to drop some of the facilities for programming the method with the presentation of chronicles. Chronicles can allow you many flexibilities with expressing parallel things and overlapping things and constraints between time. Again, this is just an intuition. I'm not saying that we have already this, but I believe this is feasible. Let me skip the rest of how to integrate these chronicles in RAI and UPOM, since this has not been tried yet, and tell you a few things about how to learn refinement method, certainly a bottleneck issue for the approach if you have to define all your method bodies by hand. So the idea here is to use as input annotated tasks, which are for each task what are the preconditions for the task to be carried on, and what you are expecting about this task. And you need also your to model your primitive actions, which can be learned. Actually, we know how to do that in many cases, which is preconditions and the distribution of probabilities of effects. And two approaches, in my opinion, are feasible. One is to rely on specified traces, as in learning from demonstration. There is a long line of research about learning from demonstration. Here you assume partially specified traces, which tells you that in this state, this task has been achieved in this trace with action A1 leading to S1 and so on, then a subtask top prime, etc. And there are a number of techniques, such as some of the techniques developed by Hector Munoz Avila, Ugar Kutter, and their co-authors in the systems called HTlearn and HTmakers. There are others as well, using goal regressions. And you need to extend that in order to generate simple methods, where their body are basically sequences of steps as in HPlan, and you have to factorize several such generated method for task into method with complex bodies. What is easily feasible is to end up with decision trees in these bodies. That can be very rich, also quite readable, and you can prove things on them, but can be generated automatically. Another option is to do learning from policies. If you have such a specification, you may extend stochastic search path planning methods to spaces of partial steps. I believe this is feasible, and this will allow you to plan through these SSP methods a number of policies. And these policies can be factored out into refinement method. Nothing of this has been tried yet. We are thinking about it and trying some of this idea I wanted to share with you. More comprehensive deliberation. I contributed to a survey paper with Felix Ingrand that developed this view about what are the basic modules or elements or component of deliberative acting agent. Here I underline mostly acting planning and a bit of learning, but there are others such as monitoring, observing, reasoning on what you have observed, but also, and very importantly, goal reasoning and interacting. These are very, very important deliberation steps that you have to integrate into a global view. And this is part of very challenging problems that I leave to you. I hope you will that you will be interested and get into that. My conclusion, and sorry of being a bit late, is that hierarchy is essential for the integration of acting and planning. Acting reactively in dynamic domains with dead ends can be costly and risky. You cannot do that just reactively. And the proposed approach about acting, planning, and learning relies on refinement method that are rich hierarchical operational models on how to perform tasks. And this is on these operational models on how to perform tasks then that you can rely in order to choose what best to do. And this is the MCTS planner. And you can have significant benefit as illustrated on some of the methods. So this approach is a proof of concept of an acting engine, receding horizon, anytime optimizing planners, and incremental learning of policies and heuristics. And there are limitations and open problems. Let me conclude by saying that the set of contributions started with the writing of this book with Denano and Paolo Traverso, and we enjoyed working together for many years. I mentioned the collaboration and discussion with Felix Ingrand regarding chapter 3 of this book, and most of the more recent work has been carried out with Sunandita Patra, and more recently James Mason. The implementation of the approach and developments were those of Sunandita for her PhD thesis. Thank you very much.